So the title of my talk is Efficient Methods for 3D Shape Comparison. And it's based on joint work with many brilliant people. Some of them I mention here, and I'll give references as I go along in my presentation. And I added a subtitle for my talk, which is Striving for Simplicity. And the main reason is in my talk, I really want to emphasize some cases where relatively simple ideas have led to interesting results and sometimes surprising insights. So I'd like to start my talk with a quote from a book that has been quite influential for me. It's a book on differential topology. And in the preface to this book, the authors say, give this explanation, and they say that the topics covered in it are usually covered in graduate algebraic topology courses as byproducts of the big machinery, the homology and cohomology functors. And there are two objections to this big machinery approach. First, it obscures the elegant intuitive content of the subject matter, and it gives the student the impression that only big machines can do mathematics. And I feel that we have a similar situation happening now where a student who goes to, for example, SIGGRAPH or vision conferences might get an impression that only big machines can do geometry processing. And I hope to dispel this notion a little bit and try to emphasize the intuitive and elegant content of this subject matter, and also kind of highlights sometimes that simple ideas can also be very useful. Of course, this is also very subjective, so maybe my a little bit more modest hope is just to share some of the insights that we had in a few recent projects. So in my work, I primarily work on creating tools for analyzing relations across geometric shapes. So relations basically are different notions of similarity and also notions of differences that might exist, in collections of either organic shapes or man-made shapes, or even shapes represented as graphs, for instance. And in all of these problems, we always try to find what are the similarities and differences that might exist in different collections. And today, I wanted to share with you three recent areas that we've been exploring. One on shape interpolation, another one on axiomatic shape correspondence, and finally on learning for shape matching. And basically, my hope is to share this observation that we made that in all of these areas, providing explicit links that connect information across different domains can result in very simple and efficient methods. And in each of these problems, I'll kind of try to emphasize what exactly these links are. So the first part is basically this problem of shape interpolation. And I think this is a very well-known and extremely well-studied problem. So it's a little bit, has this shared spirit to some of the problems that Alla mentioned in her talk yesterday, that it's very intuitive for us as humans, what you would expect, but it's kind of difficult to explain to a computer what we actually mean. But intuitively, essentially, you're given a pair of shapes like these two pink humans, and your goal is to find a reasonable or realistic interpolating sequence between them, right? And there are many, many different variants to this problem. And I would say that one of the key distinctions when you're studying this problem is, do you assume that the source and the target shape have the same triangulation? Right, so basically, whether you make this assumption or not really kind of forks which approach you're going to take. So I'm going to discuss a few of those. So there are many different approaches for shape interpolation, and I think they primarily are distinguished by different notions of shape spaces. A very fruitful way of looking at this problem is to try to embed your shapes into some space and then phrase shape interpolation as basically finding geodesics on that space. They're very kind of advanced techniques based on mesh representation, and they have some nice theoretical properties, but more often than not, they assume that the source and target shape have the same exact triangulation. On the other hand, there are more recent functional-based approaches that basically assume that you have some functional correspondences between the shapes, and I'll talk about some of these in just a few slides. And finally, there are approaches based on learning, where you basically use a lot of data to learn the appropriate shape space. And then you basically try to do interpolation in this learned, typically latent space. Right? So this is a very popular approach in machine learning based techniques. So just to highlight how this kind of learning-based methods work, I just illustrate one particular set of approaches, but this is also, I think, gives a kind of a general recipe that's used in other techniques as well. So the idea is to try to construct an autoencoder network that basically consumes unordered point sets and produces ordered point sets. So, and the structure of this autoencoder network typically is very simple. So you start with a point cloud P, you pass it through some encoder network, you construct a single vector representation for your shape, which is also called a latent representation. And then you have a decoder that basically produces another point cloud P tilde. And the main kind of the main goal that you have when you're training this network is to basically compute the weights of the encoder and the decoder networks, so that when you compare the input PI and the reconstructed output tilde PI, you want them to be as close as possible. And there are various kinds of notions of distance, like the chamfer distance, for example, is commonly used. But the key kind of property of this method is that the input should be unordered. So for example, a common approach is to use a point net kind of encoder, and the output should be ordered. And the reason why you want the output to be ordered is that you then can compare different outputs, right? And once you train such a network, of course, you can also reconstruct meshes or implicit functions or something like that. The output doesn't matter too much. And once you train this network, then you can use it for shape interpolation in a very simple way. So basically, you're given a source and target shape. You first encode, use the trained encoder to compute a latent vector L0 for the source shape. Then you compute the latent vector L1 for the target shape. And then a common approach is just to do linear interpolation between these latent vectors. So for some parameter, scalar parameter alpha, you compute the linearly interpolated latent vectors. So these are just vectors in some space, so you can interpolate them easily. And then you can decode the shape, so you can construct intermediate shapes simply by doing the decoding of the linearly interpolated latent vector, okay? And of course, if you train this properly, then you would hope that the interpolated shapes should look reasonable or realistic. Okay, so I mentioned one particular reference here of a paper that does this, that uses this approach, but there are many other papers that share the same exact spirit. And as someone coming from geometry processing, when I saw this idea, to me, it looked a little bit mysterious. And the question that I had was, why can we do this linear interpolation, right? Does it actually make sense to do interpolation in the latent space? Because in some sense, the network that you train only trained for reconstruction. So why does it make sense to interpolate linearly? So you can phrase this question as, how does the geometry emerge in these learned latent spaces? Or does it actually emerge at all? And then the other question is, does it make sense to interpolate linearly? And then more generally, can we kind of enable this type of approach for accurate interpolation, but without relying on a fixed mesh connectivity? So we kind of experimented with this just basic approach. And what you can see is that sometimes it does give reasonable results, but it can also lead to severe distortion. So here is an example of the kind of interpolation that you can get with something like a point net encoder. And you see that basically there's entire parts of the shapes missing. And this kind of makes sense because the network that you trained was only trained for reconstruction. It doesn't know anything about like shape distortion, for example. So we try to kind of think of how to avoid this or how to alleviate this kind of problem. And so I wanted to present some of these ideas. So the first idea that we had, and I would say this is a kind of a more complex idea, and I'll show another one which is turns out to be much simpler and actually works really well. So the first idea that we had is what we call operator net. And the idea is, instead of representing each shape as an unordered collection of points, we would like to represent it as a set of linear operators, or basically matrices in a discrete setting. And we call the network that takes these operators and produces the shape operator net. And basically it's kind of operates in the space of linear functional operators, right? And so just to explain how this works, basically I need to introduce this notion of functional maps. And I think that maybe for Many of you, this would be already familiar, so I'm not going to spend too much time on this. So this is like an introduction to functional maps. What is a functional map? Essentially, it's where functions from one shape to another particular basis. It like in essence looks like this. So I have a source shape M, and I can, if I have a function on this shape, I can encode it as a set of linear coefficients in some basis. So I can use scalar coefficients AI to encode it in a particular basis, and so I can stack these coefficients in a single vector. Then I can also take the same function and transfer it onto some other shape. So for example, if I have a point-to-point map, I can use a pullback with respect to this point-to-point map. And this gives me a transferred function G that now lives on another shape N. And I can also take the same function, or take this transferred function and decompose it in a basis, some functional basis on the target shape with some linear coefficients. And so this gives me another vector B. And so the functional map is simply a matrix that takes a vector A and basically translates it into the vector B. And you can show that basically when the functions are transferred using this pullback, there always must exist such a matrix C. And it actually has a simple closed form expression. And we have also other ways of computing these matrices. So what's nice is that you can use these functional maps and compute them even when shapes don't have the same triangulation. Now, a functional map only allows you to transfer functions, so transfer values of functions. It doesn't encode anything about how the shape changes or how the metric on the shape changes. So one way to see this is, for example, if you have a function f on a source shape and you compute its norm, so just the squared, the integral of the squared values of this function, then in general, the norm of this function is not going to be the same as the norm of the transferred function, right? Why? Like as an example, suppose that you have a function which is an indicator function of some region, then its norm is just the area of that region. The squared norm is the area of that region. And the squared norm of the transferred function is basically the area of the pre-image of the region, right? So basically, if you have two shapes in which like the size of the region changes, of course, the norm is not going to be the same. So like this is kind of, you know, just a fact of life, but also you can construct basically an operator D that takes functions and kind of corrects them for this change of norm. So in this 2013 paper, we introduced something that basically these operators that we call shape difference operators. I mean, this construction is very general and very universal, but in the context of shape analysis, this is useful for basically encoding distortions across shapes. So the way that it's defined is basically there's always an operator D that essentially is such that when you consider norms of functions after applying this D, they will be the same as the norms of the transferred functions. And intuitively, for example, if I have a pair of shapes and I have a function that's supported on a region that does undergo some change, then basically this D will kind of modify this function so that its norm will be the same as it would be on the target shape. On the other hand, if you have a function that's supported on a region that didn't change, then basically this D won't do anything. And there's basically a very simple expression for these operators. So we call them shape difference operators. They basically encode the distortion induced by a map. And we also have a theorem that basically the two operators, so one that kind of encodes the distortion of the area and another one that encodes the distortion of the angles, they fully encode the intrinsic metric distortion, okay? So this is something that we introduced in the shape difference paper in 2013. And then the idea was, well, can we use this for shape interpolation, for example? So in this ICCV paper from last year, what we propose is basically this kind of approach where you have a template shape and you have a collection of shapes that are all connected by functional maps to this template shape. And once you have that, then you can encode every shape in this collection as a pair of these linear operators. So they're just basically matrices. And then you can basically operate in the shape space by operating on these matrices. And what's nice is that basically these matrices, this shape difference representation of the shapes is rotationally invariant, and it only relies on functional maps. So it doesn't require, for example, a fixed connectivity. So we basically propose some very simple network for doing shape reconstruction, and we use a data-driven approach. So given a large collection of shapes, we try to basically learn a network that, given a set of shape difference operator, reconstructs the underlying shape. And what's nice is that basically you can use some standard computer vision techniques, because these shape difference operators are just matrices. They're not like collections of points. So you can even use convolutional neural networks, for example. And so, we did this, and basically then we compared what you get in terms of the accuracy, in terms of the quality of the reconstruction, using this data-driven approach, compared to previous methods that tried to reconstruct shapes from shape differences. And of course, because this is data-driven approach and it's learned, it significantly outperforms pure optimization-based methods. But even maybe more interestingly, so these shape differences, they have some nice structure. So they can allow you to solve certain problems like deformation transfer or shape analogies. And here the idea is, suppose I have a shape A and shape B, and I can measure basically the difference between the shape A and B. And say I have another shape C, and what I'd like is to construct a shape X such that the difference between C and X is the same as the difference between A and B. So for example, here we have a man and a woman in a similar pose. So if I have a man in a different pose, then hopefully I would get like a woman in the same pose, right? So this is kind of a deformation transfer. And there's a nice property of these shape difference operators, is that they satisfy kind of a well-defined product algebra. So you can show that, for example, this difference operator associated with X can be expressed as a function of the difference of operators associated with C, A, and B. This gives us a way to basically first synthesize a difference operator and then synthesize a shape out of it. And so like this property of the shape difference operators is basically something you can prove. It actually holds regardless of this data-driven approach for reconstruction. There's a different way of solving the same shape analogy problem, is basically by doing additive algebra in the latent space. So this is commonly used, and it's basically saying, okay, if I have these latent vectors associated with A, B, and C, can I synthesize a latent vector for X by doing this additive algebra and synthesize a new shape this way? And I would say that basically there's no reason for this algebra to hold, because if you just train a network for reconstruction, you might be lucky and there's some kind of structure that emerges, but there's actually no reason for this geometry to emerge. And indeed, you see that the results that you get can be quite bad. I mean, basically you wouldn't, the kind of analogies that you get are not very meaningful. Now, the same idea also applies for shape interpolation. So, like I said in the beginning, a standard approach is just doing linear interpolation in the latent space. But because these shape difference operators have a nice product algebra, you can basically use that for a kind of a more well-defined shape interpolation. And essentially what we do is we do interpolation on the Lie algebra of the Lie group of shape differences. So basically we linearize this product algebra locally, and then we do this interpolation basically in the log space. And this gives much better results, okay? So, this was nice, and we saw, okay, this is kind of a nice property. And one particular thing that I think I learned from this is that this, linear interpolation in the latent space is generally not the best idea, because you can really get a lot of distortion. But the limitations of this approach is that we need functional maps both during training and at test time, and also it's difficult to extend to point clouds because we need these functional inner products. So if I give you 2 point clouds, basically I first need to compute functional maps to a template, and that's very difficult to do at test time. So we were hoping to basically, extend this kind of similar ideas to something a bit more principled. And kind of going back to some of the contributions that have been made at SGP, there's a very nice, I think, formalism for doing shape interpolation. And it's based on a simple energy, which has been extended significantly, but in the simplest form, the energy looks like this. So suppose that I have a pair of shapes and they're represented as 2 meshes with a fixed connectivity. How can you find an interpolating sequence between these 2 shapes? And the idea is, look at basically all of the triangles in the triangle mesh, look at the edge lengths of those triangles, and measure the derivative in time of the squared edge length, and try to find a minimizing sequence, a sequence of interpolating shapes that would minimize basically the sum over all of the edges of the derivative in time of the squared edge lengths, okay, of each triangle in the triangle mesh. And you can do this because the source and the target have the same triangulation, so you can basically track every edge length over time. So by itself, this energy is a little bit weak, so you typically need to add something extra, and this has been analyzed a lot. But ultimately, I think this is one of the key ingredients for doing accurate shape interpolation. So the advantage of this approach is that it tries to preserve the intrinsic shape metric. So it doesn't just try to preserve the extrinsic embedding, but it also tries to preserve some intrinsic information. The disadvantage, of course, is that it relies on meshes that are in one-to-one connectivity, okay? So in a recent work that's just was accepted at ECCV, we basically proposed a method to extend this idea, but to point clouds, and use it to derive an interpolation method that works for point clouds that are not necessarily in correspondence. And our idea, I think in retrospect, is actually very simple. So the idea is that instead of constructing a single autoencoder that just encodes the shape geometry, the coordinates of the points, let's construct two autoencoders. The first one encodes the geometry, so the extrinsic embedding, and the second one encodes the edge lengths of the underlying meshes, which you can have during training. And so basically it's like one of these encoders encodes the extrinsic information, and the second one encodes the intrinsic information, the edge lengths. And we also have some connections between them, between these representations. So how does this work? So basically we first train a simple autoencoder network in the same way as I just described, like a point net based approach. So the input is an unordered collection of points. The output is an ordered point set. Then we train in parallel, another autoencoder that does basically that takes a set of edge lengths and tries to encode them in some latent space. So how does this work? So at training time, we assume that the shapes have some fixed connectivity, and we take all of the list of edges and we just assign some order to them. And then we pass them through this autoencoder network and then try to basically just reconstruct the same edge lengths back, okay? And we have a fixed small size, small dimensionality latent space for these edge lengths. So you can think of this network as a kind of dimensionality reduction network. And we then also train two separate networks that basically take a latent vector from the shape space and then to the edge space. So this basically like given a shape represented in this latent vector of shapes, what is the underlying set of edge lengths? And conversely, we have another network that given a set of edge lengths, construct a shape for which it has those edge lengths, right? And they're very, very simple losses to train these. And then, so this is the whole network. That's the whole architecture. There's basically nothing else hidden. And then at test time, if we have two point clouds, P1 and P2, we then, instead of encoding them in this shape space, we basically encode them in the edge length latent space. So how does this work? So we first use the encoder to construct the vector in the shape latent space. And then we use this translation network from the points space to the edge space to basically translate the extrinsic information to intrinsic information. And we do this for both the source and the target. And then the interpolating shapes are computed as just basically we linearly interpolate in the edge length latent space, and we do basically the mapping in reverse. So intuitively, we still try to construct an interpolating sequence that linearly interpolates edge lengths, but we have a way to basically go from this edge length space to the shape space through this decoder network. Okay, so I would say that basically intuitively this kind of can be thought of the first network, or this upper part, provides the space of realistic shapes, and the bottom part provides a metric on the space, right? So in a kind of a similar way as in Riemannian geometry, you have the underlying topology and then you have the metric on it. And I think this was really what was missing in basic standard autoencoders. There's no way to assign a coherent metric on them. So this extra little bit simply provides a way to measure distances between in the space. And together they kind of enable this accurate interpolation. And you can think of these translation networks as something that projects, basically, given a set of edge lengths, what is the closest reasonable shape that has edge length that are as close as possible to these given ones, all right? And so we, evaluated this very extensively and, showed that this provides a significantly better interpolation than a standard approach based, for example, on PointNet or many other existing architectures. So here we highlight the different kinds of distortions that you get during interpolation. I think the best is to show a video, so I hope that with my connection you can see it. So here's the basically the interpolations that you get with different kinds of approaches and different kinds of latent spaces. So I think one thing that I want to highlight is, for example, a standard way to avoid distortion nowadays would be to train something like like a adversarial network, and you try to discount look realistic. So you try to basically discount shapes that have some distortion. But I would quantify that approach as basically being big machinery approach. But just adding some additional metric structure on the space, on this latent space, allows you to construct very nice interpolating sequences. And again, I want to emphasize here that, of course, we don't assume that the source and the target have any fixed triangulation. They're not in one-to-one correspondence. And so they can be very noisy point clouds. So what actually even I found surprising is that using this additional edge length regularization actually even helps reconstruction. So here, what we do is we take an input point cloud that is, let's say, very noisy. And then instead of reconstructing it directly through the shape latent space, we first map it to the edge length latent space, and then we just map it back. And just using these two mappings very, very strongly regularizes the output. And then we basically get a significantly better reconstruction than standard autoencoders and these noisy point clouds. Okay, so basically, I think the main insight that I take out of this is that adding these connections between the extrinsic representation and the intrinsic representation really helps to obtain significantly better results. Okay, so that was something that we did for shape interpolation. And in the remaining part, I wanted to talk about more like shape correspondence problems. And the first one is based on axiomatic shape matching. So I talked a little bit, so I introduced this functional map representation. And so here, basically for the past 8 years, we've been working a lot with many colleagues on doing shape correspondence with functional maps. So the standard or the kind of basic pipeline that we use for computing correspondences with functional maps looks like this. So suppose that I give you a pair of shapes, M and N. So how can you compute a pointwise correspondence using this functional map representation? So it has several stages. So first we compute some basis, functional basis on each of the shapes. And typically we use the Laplace-Beltrami eigenfunctions. And then we compute a functional map of a size k by k. So basically it's a matrix of size k by k, where k is the number of basis functions. Typically k ranges, in the like 80 to 100, or maybe like 30 to 100. So it's not very large, even if the shapes are dense. And the optimization problem that we use is basically looks like this. So I'm looking for a functional map that first aligns some descriptor coefficients. So these are coefficients of descriptor functions. And there's some extra regularization that basically says that, I want these functional maps to commute with the Laplace-Beltrami operators. Now, once you compute this matrix, you can do two things. You can either convert it to a point-to-point map, or you can use it directly to transfer functions. But in the way that it's defined, you can only transfer functions that are in the span of these bases, right? And I think that something that there's been like this understanding in the community that essentially functional maps only allow you to transfer low frequency functions, because the first k Laplace-Beltrami eigenfunctions are basically low frequency, some kind of low frequency information. The questions that we had are, first of all, if there's this understanding that functional maps can only be used to transfer low frequency functions. So one question is, how can you use them to transfer high frequency information? And then the second question is, can you recover high quality correspondences from approximate functional maps? And finally, can we overall improve the refinement process, right? And over the years, we proposed many different solutions, and many people propose different kinds of solutions to these problems. So let me just give two examples. One approach is to basically, instead of using just the standard Laplacian basis and only use linear combinations of basis functions, you can also use what we call an extended basis, where you also take into account, for example, products, pointwise products of functions. So if, for example, for those who have seen Simone Mazzi's graduate school lecture, he talks a little bit about this approach. And another approach is basically, you can have a, let's say, a more advanced way of converting a functional map to point-to-point correspondence. So just to give an example, in 2018, we proposed a paper that does this kind of conversion by doing a multi-stage process with many different components. So this, we call this BCICP, for bijective continuous iterative closest point. And this BCICP, just to kind of describe how it works, basically is an algorithm that uses some subroutines, and it does many things, like each subroutine takes, for example, a pointwise correspondence, and then tries to make it more continuous, or tries to make it more bijective, tries to remove outliers and fix the maps in some ways. So there are many different stages in this pipeline. And, you know, this was a lot of work to put in place. And it seems to work fairly well, or at least it worked better than what existed before then. I think since then there are better approaches. But, you know, so if I give you a source shape and an initialization for the target shape for correspondence, then after this refinement, you get a much better point-to-point correspondence. And we also took a look at each of the components in this pipeline, and it seemed like it was important. So we tried to remove like the one stage that improves continuity. We tried to remove the outlier detection stage, etc. And so each of these seemed important. But in retrospect, it actually, I think, you know, this was kind of a little bit too complex. So in a more recent work that just appeared in 2019, we basically proposed a two-line of code algorithm that does exactly the same thing, and it seems to do it even better. And the two-line of code algorithm works like this. Given a functional map of size k by k, we first convert it to a point-to-point map, and then we convert it to a functional map of just a slightly larger size, right? And so this is, like, for example, in MATLAB, this is literally the two-line of code that you can actually just put into your program, and it would be, this is the entire map refinement method. And so we call it zoom out. And so just to give an example of a pair of shapes where we compute the correspondence either directly by using some state-of-the-art, you know, like robust functional map extraction method. And here we use functional maps of size 50 by 50. And another approach where we first compute the functional maps of size 20 by 20, and then we do this zoom out upsampling to 50 by 50, so the same size. And this works much, much better. So you see there are like fewer outliers. So all of these like issues that we try to solve directly by you know, detecting outliers, improving map continuity, you can actually solve them much more efficiently just by going back and forth between this functional and point-to-point correspondence representations. So here's a kind of a more extreme example where we took a pair of shapes, and these are shapes that we got from the Natural History Museum in Paris. And these are basically CT scans of bones of wild boars. And so this is not at all synthetic data. They have, you know, like, this is the actual meshes that you get out of CT scans, and they have different topology, I mean, very different connectivity and everything. And we start with a functional map of size 2 by 2. So this is just a matrix of size 2 by 2. I mean, it's hard to get lower than that. And using this upsampling to a size 100 by 100, you see that the initial correspondence, you know, this 2 by 2 correspondence converted to a point-to-point map looks like this if you do texture transfer. But if you take this 100 by 100 functional map and convert it to a point-to-point map and do texture transfer, then you get this result. So basically, you know, you can start with a very, very approximate correspondence, and you get a high quality result by just doing this upsampling. And, you know, this to me was kind of very mysterious, like, why would this possibly work? So, so just to give another illustration here, and this also maybe gives some intuition why I would call this zoom out. So you start with here we start with a functional map of size 5 by 5. We upsample it to 50 by 50. And here we show basically a pair of shapes, and we transfer some high frequency function. So you see that in the beginning, the transfer is very, very poor, but then it becomes more and more accurate and the local areas kind of stabilize. So, we start with the low frequency information, and then ultimately we can transfer some higher frequency signal more accurately. I would say that this method, this zoom out approach, so of course, if you're interested, you can try it out. It's very easy. It's not necessarily better than existing methods. And I think even for this BCICP, it probably gives similar results. But on the other hand, it's much simpler and in many cases significantly faster. So in our experiments, it's maybe 50 to 300 times faster than state-of-the-art techniques. And it can be used for many different problems like intrinsic symmetry detection, shape matching, partial matching, etc. So I think, even beyond the kind of results that you get, the more important, I think, question is like, is there some insight that you can gain from this? And one insight that we had is, can we basically the rationale, so for why this method has a chance of working, the rationale actually led us to try to analyze the structural properties of functional maps. And so we came up with the following optimization problem. It basically says the following. I would like to find a functional map C, but I want it to be to arise from some pointwise correspondence. So this is a very strong constraint. And we have an energy that basically says that every leading principal submatrix, so this is a matrix that you get by just taking the first R rows and R columns, every leading principal submatrix of C should be orthonormal. So typically in the past, this is very similar to energies that people have used in the past, except they were only enforcing this orthonormality for a particular size of C. But the idea here is you can actually enforce orthonormality for every submatrix of C, principal submatrix of C. And this is a very strong constraint on C. So basically, this energy is 0 if and only if the map is an isometry. And also you can basically derive the zoom out method as an iterative method for solving this optimization problem. So this was one little insight that we had. And another insight that kind of came out of this, and I think for those who have ever worked with functional maps, this might be useful as just a small observation, which is that, there's always this question of, if I give you a functional correspondence, how do you use it to convert, to compute, for example, pointwise correspondence? And one thing that you can actually so a standard approach is basically say, okay, let's take some delta functions, map delta functions, look at the images of delta functions, and then recover the point-to-point correspondence this way. But there's something that I think has been ignored, which is that basically delta functions are actually not functions, right? So delta functions are distributions, and the way that they're defined is that basically when you take a delta function, the way that it acts on a particular function is just f of x. So this is by definition, right? And so you cannot use functional maps to transfer distributions. In order to transfer distributions, you need something else. And so what that something else is actually the adjoint operator. So the adjoint of the pullback is something that allows you to map delta functions. And it has a nice property that basically if I have a point-to-point correspondence between a pair of shapes, then the adjoint maps distributions in the same direction as the point-to-point correspondence, and it maps delta functions to delta functions. And this is a small result that basically this is something that holds for any t, regardless of whether it's an isometry. And also, I think it helps to explain some of the kind of issues that people have had with converting functional maps to point-to-point maps. So this is, I would say, like, it's not even an insight, it's just a small observation, but it came out from working on this very simple algorithm, the zoom out algorithm, and perhaps might be useful for some people who work with functional maps. Okay, so this was my axiomatic shape correspondence, and finally I want to end with a small description of our recent approaches for learning for shape correspondence. And it started also with the same kind of idea of, can we identify some limitations in existing pipeline? So I described this basic pipeline for computing correspondences using the functional map representation. And, like I said, basically it has these three stages. You compute some bases, you formulate an optimization problem, and then you convert a functional map to a point-to-point map. And what you can, there's one important thing here, which is that you need some descriptors. You need some descriptor functions that you write in some particular basis. And one question that you might have is what happens if the descriptors are bad? Maybe somebody, is kind of either adversarially or just, because the parameters are not optimized, you compute some bad descriptors. Do you get good correspondences? And unfortunately, the answer is no. So basically, these descriptors are really essential for shape correspondence. So, if I start with some approximate descriptor functions like these two, so these are short descriptors. They're commonly used for shape correspondence. And if you use them to compute a functional map, and then you use, that map to map textures, you get this kind of result. So this is a very, very important component, and it's difficult to avoid it. So there are many different approaches that have been proposed for basically dealing with approximate descriptors. So adding robustness to shape correspondence. So some of them use, for example, maps and shape collections. There are some constraints for promoting pointwise correspondences. There are other constraints, and like we also worked on methods for adding better regularization for functional map computations. But ultimately, I would say that basically what we have observed is that this component, this descriptor component, is very important, and basically everything that you do is just kind of trying to get away from this problem. So there is an approach that has been proposed first in a paper called FMNet, is to learn descriptors. So the idea is, let's say I give you a pair of shapes and they have some descriptor functions D1 and D2. Let's try to modify these descriptors so they pass them through some network called FMNet. And basically let's use these modified descriptors, these transform descriptors D1 and transform descriptor D2 to basically compute functional maps. And basically you can backpropagate to learn descriptor weights here. So there's been some work on this, but the problem is you still need some input descriptors. So you start with some initial idea or then some initial descriptors that you believe are correct. So for example, typical approaches using these short descriptors, which are quite bad. Or they can be quite bad if you have a different connectivity. So what we propose is basically, let's start with just the raw geometry. So can we learn the descriptors, the descriptor functions purely from the raw geometry itself? And one like simple, kind of very, very simple, straightforward idea is, let's just take the shapes represented as point clouds, and then let's learn basically the distribution of these descriptor functions on these point clouds, but then let's use basically the basis to compute the functional maps in that basis. So here we still use the Laplace-Beltrami eigenfunctions. And one small modification that we introduced, and this is a paper that just appeared at CVPR, is we show basically how to compute, how to solve this optimization problem inside a neural network, right? So basically compute a functional map based on descriptors, but also add regularization inside a network in a fully differentiable way. And so this is a very simple approach. It doesn't use any advanced regularization. It doesn't use any kind of maps and collections or anything. And it seems to produce quite good results. So for example, we compared with many existing state-of-the-art techniques, and basically, especially when you have a small number of training shapes, it produces much better results than alternative approaches. So here are some descriptor functions that are learned by this approach. And one question that you can ask is, well, why do we even need this basis? Like if I just have the descriptors, can I just use them directly to find pointwise correspondences? And interestingly, I think the answer is no. So somehow using the basis really helps to regularize the problem. And so we actually evaluated this. So we took a look at the basically training on one data set, so this Faust data set, and testing on a different data set. And we use an approach, this 3D coded method, which is basically like it doesn't have anything to do with spectral techniques. It just operates purely on the geometry. And using this Laplace-Beltrami eigenfunction, so using this functional map representation, helps to basically gain resilience across different shapes. So it helps to generalize across different data sets significantly better. So here's one last example, one last result. So these are the kinds of results that you see basically. So this is a source shape and it's a target shape. And even with a small number of training shapes, you can get high quality correspondences, right? Okay, so this is all I wanted to cover today. And essentially my hope and my goal for this talk was just to share some simple insights that we had. And there's something that's I think interesting that emerges from this, which is that basically creating links from different domains across different domains can often result in simple and efficient methods. So for example, in this shape interpolation, we explicitly model the intrinsic information and the extrinsic information, and then we create explicit links between them. And this seems to work well compared to, for example, trying to model everything jointly. Similarly, for shape correspondence, it seems useful to have some representation that is spectral and some representation that is spatial, and try to construct links between these two. So I think there's something to investigate there, basically letting every representation do its best and then enabling connections across these different representations. Also, I think that these kind of more simple ideas, they also try to help to reveal and understand limitations of existing techniques. And something that I didn't talk too much, but at least for me, in my experience, having a basic method often leads to more insights and follow-up. So, because it kind of emerges something that you can actually analyze and you can actually prove something, as opposed to constructing some, big machine that does everything for you. So I hope this also maybe reflects on some of your work. So thank you very much. Thank you for your attention. I'll be happy to answer questions.